Hello, my name is Chen, and today I'll be presenting my research on an improved A-star search algorithm for road networks using new heuristic estimation. My project involves finding the shortest path between two nodes in a graph, which is called the shortest path problem. This is commonly used for navigation systems such as GPS routing technologies, specifically for road networks, which are a common real-life representation of Euclidean graphs. And as you can see on the bottom here, highlighted in blue is the shortest path between node A and node F for this particular graph. In this study, we'll be focusing on two shortest path algorithms, namely Dijkstra's and A-star. While both of these algorithms have the same goal, which is to find the shortest path between a given node and a target, you can see on the left side here that Dijkstra's algorithm expands nodes uniformly in all directions until it hits the target, whereas A-star on the right side here prioritizes nodes that are estimated to be closer to the destination. As you can see, this limits the search area for A-star, so intuitively, A-star should find the shortest path faster than Dijkstra's in most cases. More specifically, the A-star algorithm is essentially Dijkstra's, but with an additional heuristic function. What this means is that A-star selects the next node to expand that minimizes the value f of n equals g of n plus h of n, where g of n is the cost from the source node to n, and h of n is the heuristic value or the estimated cost of the goal. A heuristic is considered to be admissible if it never overestimates the true shortest cost from the current node to the target node, and a heuristic is called consistent if these two statements are true, where n is any node in the graph, P is a successor node of n, C of np represents the cost from n to p, and G is a target node. In the context of A-star, this means that the cost by which a node is reached is the lowest possible once that node is expanded. As an example, Euclidean distance is both an admissible and a consistent heuristic. We now introduce the k-step look-at heuristic, which we will be incorporating into the A-star algorithm to evaluate and compare its efficiency on road networks in this study. We start by demonstrating the one-step look-at heuristic using this sample synthetic graph, and we are trying to find the value of f of a where node S has already been expanded. And we do so by looking ahead to each of the direct children nodes of A. Starting with B, we calculate f of a using this new heuristic by finding g of a, which is 1, plus c of ab, which is 2, plus h of b, which is 6. This value h of b is the predetermined baseline heuristic, which in this study will be simple Euclidean distance to the goal. Adding all of these values together gives us 9. We do the same thing for node D, which also happens to give us 9, and for node C, which gives us 11. We now compare all these values and take the lowest value, which in this case is 9, so we assign f of a to 9. While this is just a one-step look-at heuristic, we can have any value of k, but this becomes less and less efficient for very high values of k because the number of steps that this algorithm would have to take increases exponentially. The current literature often compares shortest path algorithms on synthetic or randomized graphs instead of Euclidean networks, and many experiments did not include A-star when testing on road networks. In addition, many studies have used relatively small networks such as the one shown on the right side here, which are typically not representative of real-life transportation networks. Some studies have also tried comparing A-star and Dijkstra's using different data structures for the priority queue to store unvisited nodes, and one such study created the results shown on the right side here. This chart shows that for each data structure tested, A-star resulted in a shorter runtime than its Dijkstra's counterpart. So the main contribution of our work will be to apply the k-step look-at heuristic to A-star on road networks for the first time because most studies have used simple Euclidean distance as the heuristic function. Therefore, the goal of this study will be to improve the efficiency of A-star using this new heuristic, specifically by evaluating the computational performances of Dijkstra's, standard A-star, and A-star with the k-step look-at heuristic for various values of k. We will then determine which of these algorithms are best to use for different sizes of network. The networks that we will be testing on range from small to large. They are the downtown Brooklyn, Jersey City, and New York City networks, as detailed in this table shown. All of this data has come from the OSMNX Street Networks Dataverse, which is a compilation of many different road networks from across the US. And on the right side here is a visual layout of the smallest road network that we will be testing on. In the implementations of our algorithms, we test all k from 1 to 10 inclusive for the look-at heuristic. And on the bottom table here, you can see that we run each algorithm a different number of times for each network. And this is because the runtime actually significantly increases for the larger networks, and that for smaller networks, we need to record the results with a higher degree of precision. Now here are the results, starting with the downtown Brooklyn network, where we find negligible improvements from standard A-star. Specifically, the optimal efficiency occurs when k equals 2, and the least number of nodes are expanded using the 4-step look-at heuristic. As you can see in this graph, the runtime grows exponentially as k increases. And A-star with k equals 10, which is the largest value of k that we test, results in a slower runtime than Dijkstra's, but still expands less nodes. Moving on to the medium-sized Jersey City network, we find that this heuristic is more effective for this network than for the downtown Brooklyn network. This time, the optimal efficiency occurs using the 4-step look-ahead heuristic, and this is also when the least number of nodes are expanded. As you can see in this graph here, the runtime grows exponentially after k equals 4. And A star with the 10-step look-ahead heuristic is slower than Dijkstra's but expands less nodes, just like in the previous network. And finally, we get to the largest of the three, the New York City network, and here we find that 9 different values of k are improvements of standard A star. Here, the optimal efficiency occurs when k equals 8, and the least number of nodes are expanded when, again, k equals 4. Here, the graph shows that the runtime stays relatively low between k equals 3 to 8. And unlike the previous two networks, A star with k equals 10 is faster than Dijkstra's while also expanding less nodes. So the main findings of this are that the look-ahead heuristic is generally more important and effective for larger networks. As you can see on the right side here, the number of values of k that outperform standard A star increases as the network size grows. Furthermore, a larger search space or a larger network means that there is a greater need for a more accurate heuristic or a higher value of k. And this can be seen on the left side here, which shows that the optimal value of k increases as the network size grows. The limitations of this study include that the algorithms are only run on one source target pair in the New York City network, which is the largest of the three. And this is because each algorithm actually takes a considerably long time to execute in this network. We should also have a more diverse source target pair selection and use many other different networks as well. However, our results are still representative of these algorithms' performances and can be generalized to any Euclidean network. In conclusion, the k-step look-ahead heuristic does improve the efficiency of A star, particularly on larger networks. Also for larger networks, there is a higher value of k is needed to achieve optimal efficiency. As you can see in the bottom two graphs here, which show average runtime as a function of k for the larger two networks, A star with the k-step look-ahead heuristic results in a notable improvement from standard A star, which occurs when k equals 0. In the future, this new knowledge can be applied to navigation systems such as GPS routing technologies to decrease the time needed to calculate the shortest path between two given locations. To build on our work, future studies can vary the data structures used for the priority queue to store unvisited nodes in the A star algorithm with the look-ahead heuristic. Future research should also consider whether the degree of a graph has an effect on the algorithm's runtime, and should also implement a program that automatically chooses the optimal value of k given an input network. For this project, I would firstly like to thank my mentor Jesse for constantly providing helpful suggestions and guidance throughout the process, as well as my weekend lab group for all their insightful questions and feedback. And of course, I'd like to thank everyone at SSI for the outstanding bootcamp program and all the valuable learning opportunities that came along the way. Thank you very much.